Good morning, everyone, and welcome to Algorithms and Data Structures. Today, we're doing the lecture earlier at 8 a.m. And in the last lecture, we finished trees, and we saw that search trees, when they are balanced, can be extremely efficient data structures for storing, manipulating, and retrieving data. We then looked at an application towards AI, concretely decision tree learning. So we saw that this is not like an end in itself, but actually you need trees in the real world aside from an introductory course to algorithms and data structures. And we got a student who raised a hand. So if you have a question, maybe just turn on your microphone or send your question here in the chat. I'll be happy to help. And today, we'll be discussing a different, highly efficient data structure. Concretely, that's hash tables. And in order for us to discuss hash tables, we first need to discuss key value stores, then hashing, and then we can build hash tables. And we will also look at an issue called collision handling. And what we will start with is a map. In general, a map associates unique keys with values. And for example, a map could look something like this, where we have a key, which is a country name, and a corresponding value. So for Turkey, we have the currency lira. Spain has the currency euro. Greece has the same one. The United States has dollars, China has the yuan, and so forth. So we have a key and a corresponding value. And these keys need to be unique because you cannot have multiple entries for the same key. And you all have used a data structure like this in Python, concretely dictionaries, to do exactly that. And today, what we essentially want to do is we want to build our own dictionary class, because it's a little bit more than just doing the mapping like this. We'll need hash tables in order to do this efficiently. And it will take us a little bit to make it to the hash tables today, because we start with simpler data structures first. But for our map, just in general, that a map maps unique keys to values, we can also define an abstract data type for that. And the abstract data type would look something like that we have a map M, and for the map M, we can return a value that is associated with the key. So we can say M index K, and we get the corresponding value. So K would be, for example, from the example before, the country, and V is the value, in this case, the currency. However, if this key does not exist, we want to raise a key error. And in Python, for example, this would be implemented with the getItem method. And you've seen the getItem method before, for example, when we implemented array-based lists. We also want to be able to store a key value pair. And for this, we want to say M index K is V, which would either add a new key value pair or it would override an existing one. So if there's already our key already in there with a specific value, we would just override this. And in Python, we would be using the setItem method for that. We also want to be able to delete a value. And in Python, there is the del statement. And then this comes natively with Python. So in order to delete something, and I can say I delete M index K. And here I want to delete the key value pair that associates with K. And if K does not exist, so that key is unknown, I want to raise again a key error. And in Python, we can implement this with the delete-item method. There are two more methods for our abstract data type. One is the length of M. So we want to return how many items are in the map, so how many key value pairs. And we also want to be able to iterate on them. We need to implement in Python the iter method, so we'll have a chance to generate the sequence of keys in the map. It's important that we want to generate a sequence of keys in the map, not the values, but once we have the keys, we can easily retrieve the values. This is the initial abstract data type for a map. And what we see here is an inheritance tree, and we will actually start implementing our very simple map that we've just described as an unsorted table map, because we store key value pairs in there, but we don't sort them in any specific way. So we'll build this one very soon. And the unsorted table map actually is just one of many classes we're implementing today. What we also need is a map base, and the map base will be a foundation, which just contains essentially a sub or an inner class for our items. And once we have the unsorted table map and the map base, we actually want to implement our chain hash map. Later we will see what hash tables are exactly. And there are other types of hash tables. So we want to generalize the functionality of hash tables in the hash map base, and then we will have one concrete implementation. So it's 4 classes we're going to build today: map base, unsorted table map, hash map base, and a chain hash map. And in fact, our hash tables, they will internally, or at least the chain hash map will internally be using multiple of these unsorted table maps. So this is how all of this fits together. We'll discuss the theory, and then we'll see how to actually implement all of this. For this, I will switch to my terminal in a second. So what we need is first of all, we need to import something. I don't know if some of you had a look into the collections module in Python. If you have ever looked into the collections module in Python, maybe send me a thumbs up or a thumbs down if you have not done this. We haven't really used the collections module much in this course yet, but maybe just take a look at it. Can be helpful for solving some of your problems either in the course or in the future. So the collections module offers lots of features for dealing with collections, so data sets. Take a look at it. And in there is a submodule which is called ABC, and we'll discuss in a moment what ABC can stand for. And in there is the mutable mapping. This was actually something that also appeared in this inheritance tree. It was the very top class in just a figure before, and our map base will now inherit from the mutable mapping. You're wondering, why are we using this mutable mapping? So mutable mapping comes with the Python collections module, and we're not forced to use it, but we actually want to be able that when we build now our data structures, that we can plug them into this Python ecosystem. And the mutable mapping, so it's just a mapping that I can manipulate. And in Python, there are lots of other data structures that eventually inherit directly or indirectly from the mutable mapping. And if we inherit this one as well, we get some base functionality, and we can all plug it much more easy in this ecosystem. Does any of you have a clue what ABC can stand for in Python? If it actually stands for something much longer, but in Python, they keep ABC very short. Maybe a thumbs up or thumbs down if you have ever seen something around ABC and inheritance hierarchies in Python. So let me know if any of you has ever seen this and knows what ABC stands for. Only thumbs down. So, well, we got a direct message and, or I got a message, and it's something about abstract. Yes, it's an abstract base class. I guess you have all come across this term, say in your Programming 1 or Programming 2 course. An abstract base class is a class from which I cannot create objects from because it's an abstract class, but it may provide some initial features, and then I can inherit from it with a concrete class. And I have that class, I can add certain features that are missing in the abstract base class, but I can reuse the features that come from the abstract base class, and then I can create objects from my concrete class. So that's the idea of an abstract base class. And because in Python, there is no keyword in a language for abstract. If you have done, for example, Java, their abstract is a keyword. In Python, this does not exist. So it's implemented slightly differently through very specific classes, like some from this ABC world, like collections.abc, but there are a few more in Python. And this is how abstract base classes are actually realized in Python. Are you all okay with abstract base classes? Have you ever done something like this, for example, in Java or a different language? Maybe thumbs up or thumbs down if this is something you feel comfortable with or not. So most look okay. If you're not familiar with this in for example, Java, look it up. We'll now see how this can be done in Python. In our map base, all what we actually want is we want a inner class that we call item. And this inner class will just allow us to create objects for an item. And an item will be eventually just a key value pair. So when I initialize an object of the item class, I pass a key and a value, and I'm just storing them. So I'm storing in the key attribute my k, and in value, I store my v. And I want to add a couple of helper methods that will be super helpful later when we deal with items. We want to be able to compare items. And in Python, there are a couple of special methods like EQ, ending and beginning with 2 underscores, which is just the equals method. So I'm able to compare my object to a different one. And now I need to define what makes 2 item objects equal. And in for example, Java, there's also the equals method that you can implement for classes. And here in Python, it's called EQ, beginning and ending with 2 underscores, because then we are later able to use 2 equal signs in order to natively use this. And when we use the 2 equal signs, it will always map to this internal method. So, and I'm defining that 2 of my items are the same if their keys are the same. We'll later see why it's helpful that we define it this way. For now, we don't care about the value. We just say that the 2 keys must be the same. And I also want to check if 2 of these are not equal. So what I could say is I can say, for example, as before, I could, for example, write that this is not the case. So I could say I'm comparing the 2 keys, and then I'm just inverting and I'm returning this. However, I can slightly reuse what I have just done before because I don't want duplicate logic. I can just say if self, so my own object, is the same as the other one or equal, and if when I use this equal here, so the two equal signs for self and other, which are both objects of item, then this will actually map to the equals method. And then I'm just inverting the result. So here it looks fairly easy. I could just copy this logic, but imagine you're building a much more complex class with much more complex logic. You don't want to reproduce the logic, but just reuse the equal by using the two equal signs on these objects, and then you just invert this. What we also need to be able to do is we need to check if one object is less than the other one. So we want to be able to bring in some order, because later we'll need to order in a certain way these items. So we can, for example, check, is one object less than the other one? And what I'm doing is I'm checking the key, and I'm looking if the key of my object is less than the key of the other object. So this is just a very simple class, map base, with an inner class for items. We have seen we can create objects of item. We have seen we can compare them. They're equal, not equal, or less than each other. And now we continue with our inheritance tree from before. We can now implement the unsorted table map. And the unsorted table map was also in this plot from, or in this figure from before. And what we essentially just want to be able is to implement this very simple map abstract data type, where I can store key value pairs, I can read key value pairs, I can delete key value pairs, and I can get the length of the map. And also I can be able to iterate over the unsorted table map. And because our unsorted table map will eventually store multiple item objects, we somehow need to be able to use this and plug it into the inheritance hierarchy. So we just inherit from map base, and what we inherit as well is then the subclass. And we need to be able to initialize our unsorted table map, and internally our unsorted table map, it will just store key value pairs. They are not sorted in any specific way. So we are just storing them in a Python list. And we call this this internal attribute, for example, table, but it's not advanced yet as a hash table. A hash table is something we'll be doing in the next step once we have implemented our unsorted table map. And the unsorted table map will just essentially store key value pairs. We can first implement the length. That's the most simple one. And all we want to do is, if we store key value pairs, which are item objects in table, we just want to read out the length of our table attribute and return this. And the number of item objects in that list is just the length of the unsorted table map. Then I want to be able to store something. So I'm implementing them just in a different order than you find them in the slides. But in the slides, the first method that is implemented is get item. But in order to read something, we also need to know how it's actually stored. So we start with the storing, so the set item. And once that's implemented, we can actually start reading it. So we can, what we want to do is we want to set a key value pair. And we can say, well, I'm just appending a new key value pair. So I'm creating an object of class item. And I could say, I'm done, because I go to the table, I'm appending a new item object with a key and a value. what can go wrong here? Can I always just append a new key value pair or not? If you see where this may work or where there could be some issues, maybe let me know, for example, in the chat, and maybe just raise your hand if you see what the issue in said item can be so far. I got some hands raised, and one student says one issue could be that we create duplicates. Yes, because if there is already that key in my table, I cannot just add a new key value pair. So I need to overwrite that key value pair. So what I need to do is I need to go through my whole table and I need to find the key value pair that is affected. And in any case, I need to go through my table because maybe that key value pair is there already. If so, I overwrite that one. And if it's not in, I only know that once I have gone through all the items in the table. So I'm going through the items in the table and I'm checking if the key I want to set, if that key matches the key of an item. And if I have found this, so I have found an item and an item has a key that matches the key I want to set, then I just override it. I don't need to delete the item or create a new item. I just take that item that match where I have the key matching and I override the value with the new value. And then I can stop. So return means I'm not returning anything concrete. I'm just stopping or I'm just finishing the method because there's nothing else to do. I'm just done because I don't need to append anything. However, if this loop goes through all the items and there's no key match, then I'm appending a new key value pair at the end of my table. And as I've said, it's an unsorted table map, so we don't care about the order of these item objects. Later, when we build the hash table, this will be slightly more complex, but internally, the chain hash map will be using many of these unsorted table maps, but we'll see that later. Now that we know how to store something in it, we can also try to read it out. And if you by chance know, because I'm coding now quite a lot and it will take a little bit until we start executing all of this. If you ever see that there's a typo in here by chance, just ping me, because then we can fix it early. Otherwise, we'll see later when we try to execute it, if it works or if there's an error. Now we want to read an item. So I'm going through all the items. And again, I'm trying to check if an item has a key that matches. And if that's the case, then I want to return the corresponding value of the item, because we've said when I pass the key, I want to return the value of the corresponding item. So I go through all the items, and once I have a match, I'm actually done, and I'm returning this one. If this loop finishes, that means I have not found any item matching that key. So I need to raise a key error, and key error comes natively or comes as a class, as an exception class with Python. And I can, for example, raise a key error, and I just say key error, for example, for my key. And if you ever implement such, getters or whatever on your own, always make sure that you raise exceptions in case the items don't exist, because we don't want any strange behavior of our data structure that we try to read something that doesn't exist and we can still continue. We need to raise an exception here. Now there are two methods left. One is the iterator. So the iterator looks something like this. We've said we want to go through all the items in our map, and we want to return the keys, not the value, or we want to return a sequence of this. And in one of the last lectures, I think 2 lectures ago, we looked at iterators, generators, and all of this. And since we don't want to return the whole list at once, but only step by step as the iterator requests the next item, we use a generator here. We've seen this concept around trees, and now we can reuse the concept here. So we yield the item's key, and then when the iterator requests the next element, the loop runs one more iteration until it's done. And we've said we want the keys, not the values, through the iterator. Then last one is delete item. We want to delete an item for key K. And we'll have a loop now to do this. However, if the loop doesn't find that, that element, then we want to raise a key error, because if we are unable to find an item that we can delete, then it doesn't exist. So we need to raise an exception. And now what I need to do is I need to go through all the items again and try to check them and then delete that item that matches. This time I need to go through with the index, because we need the index also to have then the index where we need to be able to delete. So we go through J, which is the range of the length of the table. So it starts with 0 up to n-1. And for each of these, I need to check if K, which is the key, matches the element to which the index refers. So self.table at index K, and I want that key. And if this matches K, then I can actually just pop element J and return, and I'm done. We've discussed lists in detail. Any one of you remembers what happens if I pop an arbitrary element from a list? Is this efficient or inefficient? Maybe write something in the chat if you still remember this topic or not. I think here it's a good revision also of what we did earlier in the term. And I don't see any reactions here, but I guess you remember when I have an array-based list, I can only efficiently pop the leftmost element, sorry, the rightmost element, so the greatest index. This is the one I can pop most easy because this is just the one I drop. If I pop anything in between, then I need to move all the remaining elements from the right one to the left. And we saw this is not very efficient. We came across this issue when we tried to build a queue, for example, where we wanted to pop the leftmost element. And then we built this circular array or circular list, for example. So this one here faces the same issue, but I want to keep the unsorted table map as short as possible. If you implement this, say, from scratch and most efficiently, you wouldn't be just using the array-based list, but you would be using maybe some other data structure in order to do this more efficiently. We've seen different options, also linked lists, but linked lists come with new issues. But if you don't remember what the issue here is, that's a good revision for you to double check what we did earlier in the term. So you see, finally, all these data structures that we are building somehow fit together. And one chapter is done. It doesn't mean you don't need this anymore, because eventually that theory will pop up again. Now we have built our unsorted table map, and we can just, for fun, build a map. So map 1 It's an unsorted table map. And map 1, we can, for example, put in a key. So we can put in a 1 as an integer and say a string that says 1. Then the map 1 put in the corresponding string. We can read this now, but the 3 doesn't exist, so we get a key error. We can try to delete this, which works. If I try to delete it again, I get an error because the item doesn't exist anymore. And we see currently there's 1 element left. And we could also be using an iterator now to go through all of it. So it's not an extensive test, but seems to work more or less. We can, I don't know, create a few more examples. So we've deleted the 1. So do something like this, and we can try to read it out again. This is some auto completion here in a new version. We can also try to override it. And we see the overriding works. And there are 2 items in, because this one overrides, it doesn't create a new item. So seems pretty okay for now. And now we have implemented 2 classes. We need now, and we see we're able to build now a very simple unsorted table map. And now in order for us to make it to the hash tables, we need a little bit more theory for now. And then we're able to implement that as well. So we've obviously skipped a few slides. Now I've implemented this. It's the map base and the unsorted table map. So just to remember, we're using the mutable mapping from the collections module, from collections.abz submodule. We've implemented the map base, which includes this item class, and we have the unsorted table map done. What we want eventually are hash tables. So, and there are many ways to implement hash tables, as we will see. And we will implement a base, a common functionality, and then a concrete implementation, which is the chain hash map. And this one will be using the unsorted table map again. And all of our hash tables, they will inherit from map base. This is what we are doing now. There are a few more classes in here. For example, the sorted table map, the tree map. So the tree map is sort of a combination of a tree and a map. There are also different kinds of hash tables. This kind of stuff is explained in the book. We're not doing this in that course because they are more advanced data structures. But for the beginning, those 4 classes are enough, and we'll be able to build something that works pretty well if you test it. And we'll need a little bit more theory now, and then we'll implement it. What we see here is a lookup table. And a lookup table here has the length of 11. So we have indexes 0 to 10. And we see there are a few elements in there, a few items. So initially we built this lookup table from scratch. It's empty. It has 11 entries. So indexes 0 to 10. And for index 1, I add an element. So I add the item 1D, which I put here. The element 3Z I put there, the 6C and the 7Q. And I can just store them in here. However, this looks okay to be able to store some elements, but there could be some issues arising. Imagine we have 1,000 possible key values. So keys are possible values from 0 to 999. And I don't know upfront how many of those concrete items I'll be adding. And if if I want to store them in such a format with such a lookup table, I need to create a very large lookup table up front, and maybe I'm just storing some of these elements. So maybe the lookup table is just way too large and I'm not taking advantage of it. Maybe there will be some items that could appear with the same key. We don't really want this because we've said keys need to be unique, but maybe we want to keep the lookup table smaller, and we say we want to have keys 0 to 10, so 11 entries, but I want to be able to store more than 11 entries. And somehow I need to map the keys so that they fit in here. So maybe a certain key and a totally different key, they would still appear at the same index. So there will be some issues that we need to be dealing with. And maybe we also want a lookup table that doesn't really require the keys to be integers, because maybe the keys are just something totally different, could be a string or whatever. And all of this doesn't work too well yet with this lookup table. What we need now is a concept that we call a hash table. And a hash table uses a hash function to map keys to a corresponding index in a table. Imagine this looks something like this now. I have my lookup table, and it has indexes 0 to 10. So it has 11 entries. And there's our entry 1D, which fits perfectly fine here because it's a 1, and it has the value D. 3F as well, or 6A and 7Q, the ones from before. We've seen them, or not an A, but a C, but whatever. It looks a little bit like from before. However, there are more entries in here now. For example, there is a 14Z. And with our lookup table from before, I would need entry 14. So I would need a much bigger lookup table, which I don't want because I don't know how many of these spots I eventually need to use. So I need some function, and that's a hash function, to map the key value to an index here. And the hash function should also work for non-integer keys. So for example, if the key is a string or something else, that I should be able to map this so that it fits to one of these indexes here. This is in fact a very simple hash function because it just takes the key modulo the length. The length is 11, and 14 modulo 11 is just 3. So it goes here. 3 modulo 11 is also just 3. 25 modulo 11, so you subtract 11 and 11 again. So 25 minus 11 is eventually also 3. Same here for the 39 modulo 11 and so forth. So we see our hash function is in fact a very simple function in this example here that maps our integer keys to a corresponding index in the hash table. We would need a more complex hash function if we, for example, want to be able to have non-integer keys like strings or something like this, but we'll see that very soon. So our hash function is very simple. There are probably better ones. And now you wonder, how can I find a good hash function? One hash function could look something like this. So, for example, if S is a string, I could do certain bit manipulations with that string in order to turn it into some integer. This is one hash function, just as an example. I can take a 1, I can do a bit shift by 32 bits. I can then subtract a 1. This is just a so-called mask. My result H, the hash value is 0. I go through all the characters in the string, and I do something with these characters and using this mask and manipulating H, so it somehow gives me some integer value, which is probably a pretty large one because I move the 1 by 32 bits to the left. This is just one example of a hash function, and there are entire books or courses at some universities only about hash functions. We don't really care about this too much here. We're using a couple of hash functions in this course that the book is proposing, and they work actually quite well. We'll talk more about an issue in a moment that can appear with hashing, but we don't focus the remaining of the course on hash functions because there are lots of other people doing this, and there are extremely well implemented hash functions available for you. For example, in Python, there is a native hash function, and you can pass, say, a string, an integer, or a float value to this native hash function, and it returns you a hash value. For example, hello Deggendorf gives me this hash code. If I remove the exclamation mark, it gives me a totally different hash code. If I put in an approximation of pi, it gives me something like this. If I slightly change it, it still gives me a different hash code. So this hash function that comes natively with Python actually works quite well. So we don't need to spend the remaining of this course thinking about how to build a good hash function because it's already done for us. And now, if this was, for example, my key, for example, I need to be able to convert this into an integer index so it would fit into my lookup table from here before. So for example, that it would fit into indexes 0 to 10. So I would need to take it modulo 11. If we say I have 10 entries, so 0 to 9, I would need to take it modulo 10. And for example, my hello Deggendorf from here, it's a minus whatever ending in 3. So if I take the modulo 10, this gives me a 7. My hello Deggendorf from before without the exclamation mark, we have a modulo 10, it's then 3. We have the other hash codes, whatever. So this is actually something that looks quite good because I have 4 different keys, so these 2 strings and these 2 float values. And when I get the hash code and I take the modulo the length of my hash table, I actually get 4 different indexes. So I can actually spread them quite well throughout here. If there are entries that have the same index after doing this, I need to store them together in such a bucket. How to implement this concretely, we will see later. But the goal actually with such a hash table is, or with a hash function, is that I want to spread them out as much as possible and that they don't all fall into the same bucket. If two keys have the same index eventually, we talk about something that we call a collision. So here we would see a collision where, for example, keys 14, 3, and 25 have the same index. That's what a collision is. And with a good hash function, you actually want to reduce the number of collisions. And you want to spread this out as much as possible. If you add lots of entries, so if you have 12 entries to a hash table, or you have 12 items to a hash table with 11 entries, you will obviously have at least 1 collision, maybe more depending on your hash function, but you want to keep the number of collisions as low as possible. And now we want to start implementing our hash table. And I said we have 2 methods or 2 classes left. And the next class we want to implement now is our hash map base. And what we also need is we need something from the random package. The rand range is a helper function. Rand range, you can always look at its comment. The rand range chooses a random item from range stop. So stop is this upper second parameter, or from a different range. So what we want is we want to be able to choose a random item from a certain range, and you'll see in a moment what this is used for. And just as a piece of advice, if you ever want to, if you use such an interactive environment, be it IPython or Jupyter Notebooks, you can always just put a question mark behind, and then you get you actually get the documentation of that specific class, function, method, whatever. So we'll implement now the hash map base, and hash map base will inherit from the map base, and I need to initialize this. We have one parameter, which is the capacity, so the number of slots. We've seen this before in our example. We can say the default value is 11, but you can also pick, when you initialize it, a different capacity. Could be 10, 100, whatever. And we also need another parameter, which just helps us in the hash function when we combine this with the rand range. Here the book, for example, puts this value, but it doesn't really matter. You could also put just a different prime number. So we just use this one here by default, but it doesn't really matter for now, because it's just a prime number that will help us in order to implement a good hash function that allows us to reduce the number of collisions. What I need next is I need my table, and I need a list which has initially just none entries, and I need capacity, many of them. And we've also seen this earlier in the course. If you have a list, like this is just a list with one none element, and you multiply it with an integer, you get a new list that has that many entries, which are all none, so we're just duplicating this. And our hash map base has initially 0, or the object has 0 elements in it. We also need this prime number from before. And we also need 2 more helpers. One is the scale, and scale is 1 plus rand range of p minus 1. And sorry for all these typos. Somehow today I have lots of typos when I'm trying to code this. Hope all the typos are eliminated while I keep typing, so the code runs later. So this is the initializer. We have the prime, scale, and shift. We'll see this now, what this is actually useful for, but this is just a detail that isn't really important to this course. It's only how our hash function works. For the remainder of the course, I would always just provide you with a hash function, or we assume we have a certain hash function that works well. You don't need in this course to be able to build a very advanced hash function or something like this. We're just referring to what the book actually provides us with. But we will use our internal helper method, which we call hash function. We pass a key, and what I want to do is I want to return something. I'm using my internal hash function from Python, which already works quite okay. And I get that hash value, and I'm multiplying it with the scale value, and I'm adding the shift value on top. Now I have some hash value. I take it modulo the prime number, and then I take it modulo the length of the table. This last modulo is essential because I finally need an index that fits into this hash table. And this is one way what the book proposes to do, but obviously you can do lots of other lots of other hash functions. Probably you could just leave this one aside quite easily, or the shift, or we would just use the hash code natively from Python and take it modulo this capacity. All of this can be done, but it's up to you. Take a look in the book or online. You find lots of more hash functions that are recommended, but this one here works pretty fine. And we will not investigate further how to build a good hash function because the length of the table, remember, is just this capacity, because I have capacity many nonce initially in it, like 11 or 10 or 50. And by taking this last modulo, I will eventually get an index that fits into the hash table. What I need next is the length of my hash table, and I'm returning n because I have n many elements in my hash table. It's very important I'm not taking the length of table, because table is the capacity of my lookup table, and initially this is 11, and I want to be able to store more than 11 elements in there, because I want to build these buckets. So if there is a collision of two index, or of two keys that they have the same index, I still want to store them in the same bucket, and how to do this is something we'll see later. So here I need to return n, and here I need to take the modulo on the length of the table, because the length of the table is not the number of elements I have in total in the hash table, but it's the capacity of the lookup table. Now I want to be able to read. I want to check or get the value for a corresponding key. And we are building the hash map base. And hash map base is not able to be instantiated. So we are unable to work with the hash map base directly, because the hash map base only provides very generic functionality for a hash table. We still need to handle the collisions, and that's why we'll do later a concrete implementation of this. But there are many different ways how to handle collisions in a hash table. So that's why we have the generic class hash map base, and the hash map base will only say two things. It will take my key. It will call the hash function on key, which gives me an index j. And I'm assuming a function that is called bucket get item. And bucket get item, I go to slot j or index j in this table. And in there is a bucket. There could be 0 elements. There could be 1 element. There could be multiple elements. We've seen these buckets before in the visualization. And there, I want to get the element for key k. How to implement these buckets directly is something we'll see later when we implement a more concrete hash table. But all the hash tables you can implement, they will just come with a different bucket get item. What they have in common is the hash function and so forth. And how to manage these buckets, we'll see later in the next class. We also want to be able to set an item. And we want to set a key value pair. What we need to do initially, again, is I need to get the index, which bucket it will be in table. Then I say I'm calling self.bucket set item. I go to bucket j, which the hash function delivered, and there I want to store my key value pair. How to store this in the bucket exactly is something we'll be seeing again later when we implement the next class. What I also mentioned is there will be collisions. A collision means that two items will be in the same bucket. And we've seen the visualization before where we had 11 buckets, and now imagine I want to store 1,000 elements in there. There will be lots of collisions, meaning I probably don't have enough buckets. I should rather create more buckets and then spread out the elements better. And this is what I'm checking exactly here. I say, if the number of elements I have now is greater than, say, half the length of the table, or you just multiply it by 2 and you say, if the double, or if 2 times the number of n is greater than the number of buckets, then I will obviously have plenty of collisions, because most of the buckets will contain more than one element. Maybe all will exactly contain 2 if I spread it out well, but there could be maybe a bucket with 0 or 1 element. Other buckets maybe have 5 elements. So lots of collisions. And I don't really want this, so I need more buckets. So I say, well, I'm going to resize this, and I say I double the number of buckets. The book proposes to do something like this. I say I take 2 times the number of buckets, -1, probably the -1 we could also just leave aside. And then I'm building a new lookup table that has about the double number of buckets, and the resizing also needs to be able then to spread out these elements again. And then eventually I will have less collisions, and as I keep growing and keep adding items, from time to time I have to resize. So it's a dynamic data structure. We've seen this before as well, for example, with lists. The bucket set item will later need a concrete implementation in our next class when we think about collision handling strategies. This one will be able to deal with in case that item exists already, that I override the value. It also needs to be able to add new items, so keys that don't exist yet. And the bucket get item will return us a corresponding value, but it also needs to be able, in order to, for example, return a key error in case that item doesn't exist at all. But this is things we'll see in the next class. Then we need 2 more methods. One is delete item. As before, we have a key and we want to be able to delete that item. So I again need to find the right bucket. And I need a method that I call bucket delete item for the bucket J and the key K. I'll delete it. And once it's deleted, I will reduce n by 1. The n by 1 is something we're keeping here in the hash map base, because then in general, we reduce this by 1. And how to delete it exactly in the bucket is later implemented in a concrete implementation. But this one here is a generic one. Otherwise, I need to copy that line into all the concrete bucket delete items. And then we need resize. And resize means I have a new capacity C, and I want to create a new lookup table. We've seen this before with array-based lists. I somehow need to keep the old data structure, then create a bigger data structure, and then copy all the elements in, and need to delete the old data structure. So what I'm doing here is, it's called .items. Self.items is something we'll see later. Self.items gives me essentially all the key value pairs. So .items is something that we got from this inheritance hierarchy, because we've inherited from MapBase, we've inherited before from the other class that was named immutable mapping, and the items comes from the inheritance hierarchy, and it essentially will later give me, or I will have an iterator that will give me all the key value pairs, and I'm copying this totally. That's why I call list on this iterator, and I get all the key value pairs into this list. So this is the old data. I have stored this now in old, and I need to create my new list of the new capacity C. I say my N is now 0 because N will be increased when I'm re-adding the items, because when I'm setting the items internally, the bucket set item, for example, will increase N. And in order to make sure that N is not inconsistent, we set it now to 0, and then we keep inserting all these key value pairs from old into my new lookup table. So I can say self index K. This will call set item with key K and value V. So we have now implemented the hash map base, and all we need next is one concrete class in which we specify what bucket get item, bucket set item, and bucket delete item should look like, plus what the iterator should look like. And then we're done with implementing all of this. I will quickly go back to the slides to show you where we are in this roadmap now and provide you with a little bit more theory. So this is what we have just implemented. And the challenge was that we have our hash table. We have these buckets. So we have the buckets here, 11 many. And the resizing is necessary when we store lots of elements in here, so far more than 11. Then I will have obviously lots of collisions because I keep adding more and more elements to these buckets. And this will reduce efficiency because the hash table, we will later look at the complexities, is a highly efficient data structure if I have enough indexes. If there are some collisions, it's okay. However, if I'm trying to store, say, for example, hundreds of elements in here where I have 11 buckets, this will become quite inefficient because I can do the lookup very easy. So which index, but then I need to go through a bucket that may be very long, and that's inefficient. So at some point I need to resize, and this is what we have just implemented. Resizing means I create more buckets, and then all these existing elements, they will be spread out in this new range of indexes. And because the hash function also considers in its modulo the number of buckets I have, I will redistribute all these elements, and they will probably appear in a new bucket. But then I will have far less collisions. And if I keep adding and adding, at some point, I will have to resize again. Are you all okay with up to here? Maybe thumbs up or thumbs down. And if there are any questions, let me know, because we have one more class to implement. So only positive reactions so far. And yeah, this is the hash table. And our goal is simply now to have concrete implementations for how to deal with a bucket. One thing I forgot, I said before in the resizing, then the old data structure will be deleted. So I'm copying all the past elements into old. I'm resetting this table. I'm inserting the elements. And in Python, you don't need to manually delete this because it's just anyway a local variable which will disappear when the resize method is returning or when it's done. And then this one here is somewhere stored on the heap but there are no more references to it. So the garbage collection in Python would just clean all of this at some point. If you implemented this in Java, it would work exactly the same because of the garbage collection. If you implement this in, I don't know, C or C++, you would manually need to keep track of freeing the memory. We've already talked about collisions now a few times, but I have, again, a formal definition of collisions. So if we have two keys, K1 and K2, and their hash values are the same, so we have distinct keys, but same hash values, then I have a collision. We have so far, in an abstract way, dealt with these buckets, but the question is, how can we concretely implement these buckets? So how can we concretely handle the collisions? And there are different collision handling schemes described in the literature. The two most common ones are separate chaining and linear probing. In this course, we'll focus on the separate chaining because I think that's the one that is also used most often in practice and probably the one that works most efficiently. Linear probing is also okay. I'll later show you just a brief slide about linear probing, and we will implement the separate chaining. And if we go back to the very beginning of today, I had this inheritance hierarchy. Remember, we have just implemented the hash map base. Before, we implemented the unsorted table map and the map base. And now I said, in our hash tables, we will always just deal, we have just implemented this very generic feature of dealing with buckets. And when we inherit now in our chain hash map, which does the chaining, we inherit all the functionality from hash map base. So just the last class we have implemented. But some methods are missing, like how to implement the buckets exactly. So we need to provide this in chain hash map, and we inherit all the features we have just implemented, like get item, set item, and then we can create objects of chain hash map, and it will work perfectly fine. The probe hash map is a different class proposed in the book. It's about the linear probing, a different collision handling scheme, and there you would also just implement these three bucket helpers in a slightly different way. So the separate chaining looks something like this. Before we've said, when we have our buckets, or we said we have buckets here, and somehow we're just putting all these elements in, but in the separate chaining, I say I need to bring in some concrete ordering in there. And what it looks like is you're adding an element, for example, 18. And 18 is a key. So we only visualize here the keys. We don't visualize the values because we only care about the keys right now. But each key actually here is an item object with a key value pair. And I'm storing 18, and 18 is mapped to index 5 through my hash function. The hash function would just look something like, it's the key value modulo 13, just a very simple hash function. Then I put it there, but I'm not putting it directly into here, but actually I'm creating an object of the unsorted table map. And in the unsorted table map, I just put in the 18. I'm doing the same for the 10, which is mapped to 10. But then, for example, element 36 or key 36 is also mapped to the index 10. But at index 10, I already have key 10 in this unsorted table map, and then I'm just appending the 36 to the unsorted table map. So I'm just adding this as the next item in the unsorted table map. And it's the same with 54. 54 is mapped to index 2. I'm storing it there in an unsorted table map. Then the 28 is also mapped to 2. So I'm storing this as the next element after the 54 in the unsorted table map. The same for the 41. So we see when I have a key, I'm finding the corresponding index, and then I'm just looking what's in at that index. For storing, if there is nothing yet, like for example at 8, I would create an unsorted table map. and put that key as the first entry, the next entry later, and so forth. And when I read out, I would read my key, put it in the hash function, get a corresponding index. And if there is just one element in the unsorted table map, I would look at that one and see, is that the key I'm looking for or not? If there are multiple entries, I may have to go through all these entries in the unsorted table map. Unsorted means linear time. So if the unsorted table map is super, super long, this will become super inefficient because I don't have any ordering in here. But if I have a good hash function, I will spread out the values very efficiently throughout these indexes. And I will typically just have very short unsorted table maps where I just need a few lookups in order to look this up. And then it isn't that inefficient. Then actually it's quite efficient, and we'll see the complexities later. And that's why at some point, if I have a lot of elements in this data structure, I need to resize. And by resizing means I would, for example, double this to 26 or 25, whatever indexes. And then I will have much shorter unsorted table maps because all these elements get redistributed. And then the lookup will be cheaper again. And I'll show you now how we can implement this concept of an unsorted table map. And today the lecture will take a little bit more than 90 minutes. I had changed the announcement in the iLearn news because then we're able to finish the hash tables in one lecture. So we'll need maybe today another 15 or 20 minutes, but then we're done and we don't need to restart in the next lecture because then we have fully discussed this topic. So the chain hash map inherits from the hash map base. And we've seen I need to be able to get the item. I need to be able to set the item and need to be able to delete it. And we'll implement now the bucket get item. And the bucket get item, we get J, which is the index. So in which index in the hash table, and then the concrete key K. So I can get the bucket and I can say what's in the table at J. It's the index J. And if the bucket is none, so if there's just nothing in it, it means there are no elements at that point. So I can raise a key error because if there is nothing in that entry J, then I'm unable to find my entry, because if my entry that I want to look up existed, it would be in that entry, but there is nothing. So I'm raising a key error. However, if this condition is not true, then I'm not raising the error. And then I can just say, well, return bucket index K. And my buckets are instances of the unsorted table map. And we had implemented today as the second class, the unsorted table map. And there we had put a get item method. So I'm able to read index, or I'm able to put in index or key K. And I went through all these items in the unsorted table map, and I tried to find that entry. And if it didn't exist in the unsorted table map, I would raise at the end the key error. This is something what we implemented like an hour ago. Then I need my bucket set item. And for set item, we have said we pass our index J and the key and the value. And first of all, I need to check if the table at index J is none. So if the index is J, it means I have to store it at index J, but if it's none so far, because initially I'm initializing the whole table just with none entries, that means I need to be able to store the item there, but my convention is I'm always storing the items in unsorted table maps. So I can say my table at index j is now an unsorted table map, creating an object. Then I need the old size. I'll show you in a moment why old size is stored here. We first type it. So the old size is what I'm taking is the length of the unsorted table map. Then I'm storing my entry. So table at index j is then the unsorted table map. And I'm looking up the index k, which is the key. And we've seen this before. When we implemented set item in the unsorted table map, we had a set item, and with the index k, we're calling this set item, and it will either overwrite an existing item or an existing item's value, or it will append the value. We had implemented that, and now we're implementing this concretely in the set item. And I had my old size. And now I want to check if the length of the table at j is greater than old size. If that's the case, I'm increasing n by 1. You're probably wondering why I'm not directly increasing n by 1, but I'm first checking the old size, and I'm checking if this one went up. There's a small corner case that could be appearing, but take a look at the book if you're curious why I'm first taking the old size, and then I'm checking the new size compared to the old size, and then increase n by 1. But it doesn't matter for now. Just for the super curious that want to look it up in the book. And we also need to implement how to delete an item. So at index j, we want to delete our k. And what I need again is the bucket. And I can check if the bucket is none. So I want to delete key k. I check in which bucket it would be stored. If there is no bucket, that means there is nothing at that index. That means the element cannot exist. So I'm raising this as an exception. However, if there is a bucket, I need to delete my key k from the bucket. And when we implemented the unsorted table map, we also implemented the del or the delete item method. And that's why I can call delete on bucket with index k. And in terms of code, there's just one method left. It's the iterator. And with the iterator, what I want is I want to yield the items, and our convention before in the unsorted table map was that when we yield or what we want to pass to the iterator, we said always the keys, not the values. And this is exactly what we are doing now in the hash table. I'm going through all the buckets in the table. And I need to check if the bucket is not none, because if the bucket is none, then I'm unable to yield anything there, because an empty bucket, I can just go to the next one, because if it's empty, that means empty here means there's no unsorted table map in the bucket. So I'm just looking at the buckets where there's actually an unsorted table map, and then I use a generator delegation, and it's the yield from bucket. And yield from bucket, we've seen this syntax 2 lectures ago when we looked at generator delegation on trees, and yield from another generator. And the generator from bucket is the iter method we implemented for the unsorted table map. So that's another generator, and that's why yield from for the generator delegation. So we have now implemented our hash table, and we can just test it. We could just call it ht1, and we create an object of the chain hash map. We see initially there are 0 entries in it. ht1 at index 1, we can say as a string 1, ht2, ht1, here is the 2. Now we have 2 elements in here. And try to override this. We can also try to read it out, and we can also try to delete something. So this very simple initial test seems to show that it works. Obviously, feel free to test it in greater detail. And you're probably wondering, what is so different now about this compared to just the unsorted table map? We've done similar tests for the unsorted table map, but remember, the unsorted table map is quite inefficient because I'm just able to store items in an unsorted way. So looking up is quite inefficient. But now if we integrate those into our chain hash map, so our hash table, we can actually do the lookup super efficiently, because we just need to find the index through the hash function. And then we probably have just a few elements in the unsorted table map there, and then the lookup is quite efficient. But we'll look at the complexities in a moment. And feel free to test this in greater detail. We've implemented now 4 classes. I know it was quite some code, but eventually it all fits together. And I'll just show you again the inheritance hierarchy, that we are all on the same page of what we have done today. So we said we implemented the map base with the items object or item class. So we create the item objects. We wanted a hash table, but we somehow need to deal concretely with the buckets. We've chosen that we use the chain hash map, and the chain hash map uses at its indexes objects of class unsorted table map. There are other approaches like linear probing, which is another approach to dealing with these buckets. The linear probing would try to insert an element, and if that index is already taken, it would just probe to the next entry and try to put it in there. This is something that is called linear probing. It's just the other class in the inheritance hierarchy. We have not implemented this now, but feel free to look it up in the book in case you're curious about how linear probing works. But for the remainder of the course, we only care about the chain hash map. And what's also important for the remainder of the course and also towards the exam, you don't need to be able to propose a very advanced hash function that has a low number of collisions. We have simply just used one way that is recommended in a book to build a hash function. You need to know what a hash function is and maybe apply a very simple one, but you don't need to be able to propose an advanced hash function that has a low number of collisions. If we now look into the complexities of what we have done and compare this to a list. So just a traditional list, if like an array-based list. If the elements in there are unsorted and I want to get an item or well, maybe we'll look at that in a second. At the get item, maybe we start with the length and iter. Iter is obviously for list and the hash table O of n because I want to read out all elements. Getting the number or the number of elements is O of 1 because in our list we're just storing this as well as in the hash table as an attribute. And the hash table has quite some advantages over a list. And the hash table is a very efficient data structure. So n is the number of items. And if I want to read out an element from the hash table, it's expected that this takes O of 1 because I have the hash function, which is super efficient and gives me an index. And in the best case, there's just a single element at that index. And I can just read it out. In the worst case, there could be multiple entries at that position, but probably in practice, just a very short unsorted table map. So I need just a few steps in the unsorted table map to read out my key value pair. And that's why I say expected is O of 1. In the worst case, it's obviously O of n. If I have a really bad hash function and I'm just super unlucky and almost all the elements are stored in a single unsorted table map from before, and that I'm not really able to spread out the keys, but I'm storing almost all elements in one of these buckets, then it's obviously O of n. With a list, trying to read out the value for a specific key, and I just have this unsorted, then it's obviously O of n if I don't have any structure in the list. Same for setting an item. Adding an item is probably fairly easy. Overriding an existing element is more difficult. That's why the list says O of n, because I need to go through all these unsorted entries and try to find if there's one for my key already. And if so, I override it. If not, I append it at the end. And with the hash table, it's also expected to be O of 1 because I find the index very efficiently. And then maybe there are no elements at that index, then I can easily add it. Maybe there are a few elements in this bucket at that index, but I can probably just go through them very quickly because it's just a few of them, assuming I have a good hash function. In the worst case, it could obviously still be O of n because maybe I'm just very unlucky with the hashing and almost all of my elements are in a single bucket. But this is rare, and assuming I have a good hash function, this is unlikely to happen. Theoretically, it could still happen, and that's why worst case is O of n, but expected it's O of 1. And it's the same for the lead item. If I have these unsorted elements in my list, I need to go through all of them and try to find that one to delete, or at the end I see it didn't exist, so I'm unable to delete it. And with the hash table, I get the index through the hash function very efficiently. If there's nothing at that index, I can just return the exception. Maybe there are a few elements that I need to go through, either delete the one or then raise the exception, but it's fairly easy to do this. Still, worst case O of n, even though it's unlikely. So now that we've discussed the hash tables, do you see that they are in fact an efficient data structure by using this hash function, having an index, and then typically just a few elements at that index? Is this something you have started to understand from today's lecture, that we have built a super efficient data structure? Maybe thumbs up or thumbs down. So I'm getting positive reactions. I know we've written quite a lot of code and 4 classes that all fit together. This will take you a little bit of time for revision. I know that, and it's important you take this time to understand it. Hash tables are a very efficient data structure for storing, manipulating, and retrieving data. Trees are another approach. So search trees that are balanced, they are also efficient. And trees are just a totally different approach than hash tables. Depending on your use case, you would pick the one or the other one. But you have used the dictionary class many times in this course already. And each time you use the dictionary class in Python, this is just a hash table implementation that comes with Python. It's probably still a bit better than the one we have implemented today, because we have built like a simple hash table. We have used the unsorted table map internally. We've seen that deleting from the unsorted table map wasn't that efficient by using the pop. So the dictionary class in Python is probably still more efficient than yours. Maybe not in terms of the complexity, but in the terms of the concrete running time. Maybe feel free to test this with a bigger data set and see which one is more efficient. But I think just within 90 minutes, we have built quite a good data structure, and it's a fairly helpful data structure. It works different than a search tree, because a search tree stores the data in a sorted manner, because we bring in order in the tree and then can look up efficiently. We need to make sure that the tree is balanced. And here with a hash table, we're not storing the data in any sorted way. Rather, we use hashing. And what's crucial here is, like for a tree, a search tree, it's crucial to have balance. Here it's crucial to have enough buckets, plus to have a good hash function, so we reduce the number of collisions. I'll share a few more tricks with you and a few more sentences for the last few minutes. And for this, I will share my coding environment. Imagine you have a dictionary in Python. So you can initialize a dictionary like this or like this. And you want in your dictionary something like, say, key 1 and then key 2. And you want to store a value. So value, something like this. Have you ever tried to build such a nested dictionary? Maybe thumbs up or thumbs down if you have ever tried to build a nested dictionary in Python. So I would have one key and then another key or a third key. So one person has tried to build it. Maybe you can share with us in the chat or turn on your microphone what you have tried to build with a nested dictionary. And I'm just curious to find out what you have used it for. And what do you, like all of you, think, does this line of code work or not? Maybe thumbs up if you think I can build a nested dictionary like this, or thumbs down if you think it doesn't work that way. Thumbs down. And yes, this does not work. And the student from before, maybe just share with us in the chat or in any other way, turn on your microphone, what you have used it nested dictionaries for. So this does not work because initially I just have a dictionary and I can store values in the dictionary, but not sub-dictionaries. So what I need to do is I need to say, I'm going to key 1, and there I'm not assigning a concrete value, but I'm assigning another dictionary. And then I can say, well, I'm taking key 1, then I'm in the sub-dictionary, and there key 2, and for that I'm storing this value. And then I have built a nested dictionary. So we plot it here and we see key 1 refers to a sub-dictionary. But it's quite bothering that in between I need to build this sub-dictionary myself. And that's not fun, especially if you imagine you have a very complex data structure with lots of dimensions. So you need to store this in such a nested dictionary, but building all these intermediary ones is quite bothering. So Python comes with a solution. It's called a default dictionary, and comes also with the collections package or module. So collections.default dictionary is it's a different dictionary. It's a default dictionary. So by default, when you build a nested dictionary, in between, it will create you the intermediary dictionaries. The default dictionary is something far more powerful. You can use it for lots of other things, not just for the use case here, but then I can directly store this. So the default dictionary says I have a default dictionary, and by default, it works on a dictionary. And then as a consequence, it creates these intermediary dictionaries when I want to assign a key value pair. You can use the default dict for many other things. We can, well, it's collections, the default dict. Also has this documentation. You can do much more with it. And if you're curious to see what's in the collections module, you can also just look this up. So the collections module has lots of other things in it, not just the default dict or ABC. We've dealt with this, the abstract base classes. It has a name tuple, it has a counter, a chain map, lots of other extremely helpful data structures. Maybe look this up. It's not necessary for the course to find out in detail what the collection module offers, but can be helpful for your future career. And your classmate has now also sent me a message, or all of us here in the chat, what he has used the nested dictionaries for. And he has stored JSON data in his dictionary. And yeah, JSON data can be represented very well with a default or with a nested dictionary. Last slide for today here is there are lots of further types of maps. There are sorted maps, so to store the data in a sorted order. The whole concept of sets or multi-sets. So a multi-set it's an extension of sets where you can actually store the same item multiple times in it, but you can still do an efficient lookup like in a set, or tree maps. All of this has to do with maps or hash tables, so sorted ones, sets and multi-sets. So you use essentially some hashing in order to represent or look up in a set very efficiently, because we don't care about the order in a set. And tree maps are a combination of trees and maps. For these topics, you can find more chapters in the book, but that definitely goes beyond this introductory course. But if you want to study these data structures in detail, look them up. They're explained in the book, but there are anyway also implementations available of this in Python or through other libraries that come in a Python ecosystem. So you don't need to be able to implement this from scratch. But today we have started, or we have started and completed to build our own hash table. There is also coursework for all of this. And the coursework is here in section 13, maps and hash tables. So there are a few exercises in here. And to do some exercises, what I have shown you today is you don't need to copy paste this from the slides, because this typically leads to lots of issues when you copy paste from a PDF. In our Nextcloud, we have the resources.zip file where you find all these classes from today available. And I want to say a few words about the coursework, because I got a few emails and I promised I would answer this here. There's a little bit of confusion between the mandatory and the exam bonus problem. So the mandatory problem refers to P 13.50. This is the Goodrich book, because P whatever I always write from the Goodrich book. This is a comparison of 3 pattern matching algorithms. You would implement this in a Jupyter notebook. And if you need help with Jupyter, let me know in the lab. And what I want you to submit is an HTML export or a PDF export, whatever. So you would implement the code in the Jupyter notebook, plus some examples and some plots and all of this. And you also need to write a report. The report is the report ideally would be included directly in the Jupyter notebook. So you would write some text and documentation in the Jupyter notebook. And then very importantly, don't submit your Jupyter notebook through iLearn, because I don't want to run it because of cybersecurity issues. Rather, that's why I require that you submit an HTML export of the Jupyter notebook in which you have run all the code and visualized the results. You can also submit a PDF export, whatever. Take a look in Jupyter notebooks that you can export them. Don't submit the Jupyter notebook. And there is an exam bonus problem. And this one here says problem, so not P, I know problem 12.6. And this is a problem here from the coursework sheet. So I know it's maybe doesn't help from the distinction P or problem, but all these P whatever are always from Goodrich, and problem 12.6 is here from the coursework sheet. And I want you to implement the decision tree learning and run it off a training set of your choice. This is the problem. And for the exam bonus, you get a 10% bonus for the exam. So you can substantially improve your mark. But you would implement this algorithm, and you would also pick a training set of your choice, and you also need to visualize this learned tree, ideally in an automatic way. So if you change your data set, you generate a different tree, your visualization would also update. So not a hard-coded visualization of a specific tree. And you have about 4 weeks left for the submission of all of this. So everything needs to be submitted until June the 29th. You can either do this alone or as a group. And if there are any problems with this, let me know in the lab. For today, we're done with this lecture. Concretely, we will have 2 lectures left because we're advancing quite rapidly. We have 1 lecture on selected topics, which are selected algorithms and data structures. And that's quite a big chapter. We're picking some of it. We're not discussing all of these algorithms. Concretely, we will probably pick the fast matrix multiplication and one of the other ones. I don't know yet which one. There are lots of selected topics in this chapter, but the ones we pick, only those are relevant to the exam, obviously. And then we have 1 more lecture on quantum computing. And at the end of the term, we have a 3rd lecture, not with new content, but to discuss last year's exam. But that's in a month or so. We will be discussing last year's exam together, but I'll also send an update. So as usual, we'll have a lecture next week to discuss the selected topics. Next week, we are also back on campus for the labs, because now this holiday season is over. That has severely affected us, and we're doing the labs and lecture as usual next week. I will stop the recording now, but I'm staying here for the online lab in case you have any questions about the coursework. Even though today is a lecture-free day, I said I'll be here for the lab online. And I'll see you next week at the lecture.